All right, this is 10.3 heat capacity. So far we've been talking about changes in temperature, changes in how things expand and contract when they're heated, and the different temperature scales that we have, Kelvin, Celsius, and Fahrenheit. There we go. So now we're going to look at heat capacity. So you want to make sure you know the definition. We talked a little bit about this at the end of the last video, that at one time people thought heat was considered more like a fluid because it could flow from one place to the other. So they gave it the name caloric. And that's where we get the units of heat, calories, from. Experiments later found that that's not true, that it's not an actual fluid. It's just another form of energy. And so if it's a form of energy, it has to abide by the law of conservation of energy. All right, so here is just an illustration of how we transfer heat and how that heat can then be used to do, or that energy can then be conserved and used to do work. So we'll come back to that later. So we're measuring the mechanical work and the increase in the water's temperature. Joule showed that you should be able to, that energy was in fact conserved. So it doesn't just, it flows from one thing to another, but it's not lost. It's not destroyed, because that would go against the law of conservation of energy. So Joule proved that with his little experiment that you saw in the last slide. It established what was called the mechanical equivalent of heat. The mechanical equivalent of heat is the precise amount of mechanical work that has the same effect as the transfer of a given amount of thermal energy. And that translates to 1 calorie is equal to 4.186 joules of energy, or 1 kilocalorie is 4,186 joules of energy. Okay? And that is just basically the amount of work that could be done by transferring that amount of energy, heat or thermal energy. Oops, there we go. The units for heat are measured in calories or kilocalories. And that the specific heat of something is defined as the amount of heat needed to raise the temperature of 1 kilogram of water, 1 degree Celsius. So that's our official definition of heat capacity, the amount of heat needed to raise the temperature of 1 kilogram of water, 1 degree Celsius. That would be 1 kilocalorie. The calories that you use as far as counting calories in your food, that's a capital C. And it's basically the equivalent of 1 kilocalorie. Heat is given the symbol Q. And again, it can be expressed in joules or calories, whichever one the problem happens to give. Heat is a positive number when the thermal energy is added to the system, and it's a negative number when thermal energy is removed from the system. So Q is going to be positive if we're adding heat to the system or thermal energy to the system. Q is going to be negative if we are taking thermal energy away. The specific heat capacity of a substance is the thermal energy required, again, to raise the temperature 1 kilogram of that substance, 1 degree Celsius. So that's specific heat. How much do I have to put in? How much energy do I have to put in to raise the temperature 1 kilogram of 1 kilogram of that substance, 1 degree Celsius? So different substances have different thermal energies for a same change in temperature. So they have different heat capacities. So every substance will have a little bit different heat capacity depending on what it is. Substances with a high specific heat capacity require a lot of energy to show any change in temperature at all. And water is one of those things that has a very high heat capacity. It doesn't change temperatures very quickly. So if you look at the two analogies they have there, the bigger your vase, the more water you can put in there. So a vase with a large capacity of water is like a substance that has a large heat capacity. You can put a lot of water in there before it fills up. Whereas if it's a smaller diameter, it's going to fill up a lot faster. Okay, so here is what heat capacity is equal to in the form of a equation. So specific heat capacity is represented with a lowercase c, and it's just the amount of heat, Q, that has to be put in to change the temperature of 1 kilogram of a substance, 1 degree Celsius. So to determine specific heat, we take the heat and we divide it by the mass of that substance times its change in temperature. And that gives us our specific heat. And the units are joules per kilogram degree Celsius is the one we'll probably use the most. So here's the table of specific heats. You will either be given this table or given the specific heat, or you will be given the heat, the mass, and the change of temperature so that you can use that to solve for specific heat. Water, as you can see, has the highest heat capacity out of this list, and that's what accounts for water temperatures being nearly constant wherever you're at, especially in a large body of water. So the ocean temperatures and stuff don't change a whole lot with the change in the seasons. All right, so how we can measure heat capacity. We use a instrument called a calorimeter, and a calorimeter is just basically measuring the energy conservation. So it's something that's going to be insulated, so you'll have a certain temperature of the substance in there, you'll put in a new substance, and you'll measure how the temperature changes over time. So if we have a heated block of a metal that we have known mass, but we don't know its specific heat, all we have to do is put it in the calorimeter that contains water with certain mass and certain temperature. And then after equilibrium has been reached, that's where both things are the same temperature, then we can look at the final temperature of the metal and use that to determine the specific heat. And we'll actually be doing that experiment in this chapter. So specific heat is then determined by equating the loss of energy by the block to the amount of energy gained by the water. And we can measure the temperature change in the water very easily. So whatever temperature change occurred in the water, that came from the loss of energy in that block. So they're the same number, different signs. And that is it for section 3.